So today is the second lecture of calculating in EFT. Now, if you forgot, last time we saw this little quantum mechanics example that had all of the physics in it, but not all of the calculational complications of QFT. So now we will go to the real thing, to QFT. We are high physicists after all, but it's good to keep that example in mind and see what are the aspects that we're going to highlight in each of these lectures. So today it's going to be matching, basically, this connection of the UV model with our expansion in small distances or large scales. To set our notation and terminology, we look at a energy scale in which energy increases. We have some high energy scale lambda, capital lambda that is, which is the inverse of a small length, so it's a large number. That's where our UV model lives, ultraviolet. I will characterize it by the action, the four-space integral of the Lagrangian density. And we'll call that SUV. And below that scale, a typical energies K, remember natural units, so momentum equals energy, is where our EFT lives. And it has its own action that we'll call SEFT. So today we'll work in this line, lambda, matching the two theories and obtaining from an ultraviolet model or an ultraviolet action the effective field theory action that follows for a number of models. The models that are in store for you will be somewhat of increasing level of complexity. We'll start with something that is sort of the poster child of these type of problems, the standard model W bosons and Fermi theory, to then go to the central EFT that we'll use for the rest of the lectures, a complex scalar. Keep it simple in that sense, and that's the one theory we'll work with over and over. It'll be good to get to know it in depth. But for now, let's start with Fermi's theory. You know, this is the theory that gives us nuclear beta decay that we had knowledge of back 100 years ago, and that only later on we found out where it comes from, really. So, knowing what we know now, the ultraviolet action for this theory is given by the interaction with W bosons, that I can write as follows: W plus mu partial square, that's the W's mass squared, W minus mu, and the coupling to a current E over square root of 2 is a proportionality constant by definition of W, let's say, plus, or let's say what I say in the notes, minus mu. And because that is not self-emission, we also add the emission conjugate. I'll write as HC, now and forever. A few notes in here. Well, I hope you don't get confused. Partial square is partial mu contracted, but it saves me a bit of ink if I write it like that. We have that the emission conjugate of W plus is W minus, the fields, and that the current J minus is made out of fermions, so it's minus is for the electric charge, so that will be U bar gamma mu P left P plus mu bar gamma mu P left, and the electron. Yeah, I hope you know a bit about Dirac matrices and P lefts and P rights. Those are the projectors with gamma 5s in them. But this is sort of the only fermions we'll be seeing in these lectures. Whereas the action for the EFT, what we see are low energies, and something else for me to say, sorry, is that in this instance, because we're not interested in electromagnetism, but in fact, you should promote this partial derivative to a covariant derivative because the W is charged under electromagnetic interactions, but it's not relevant for us. So in here, I'm setting alpha, the weak structure constant, to 0, if you like. If you like or you don't like it, I'll just do it. And then at the low energy EFT, if I want to be consistent with that, I'll just say that we have a sort of a leading action that is QCD. You could add electromagnetism in there, is what we see at low energies, but again, we're looking at weak interactions. And then Fermi's term, which is in the funny conventions, one uses 4 over square root of 2 of G Fermi and those currents. Do I write it like that or like this? Yes. E and then E bar mu, E left, E. Good. Keep my time, sorry. There we go. And this is again not self-emission, so we add the emission conjugate. Righty, 2 theories. We'll derive the Feynman rule for each of them and match them. That's the task at hand. I don't want to run out of room too much, but let's try to keep it brief. So maybe I'll put it here. For the UV theory, the Feynman rules we need is how the W interacts with that current. So let's say if there's a, can you see the blue color okay, by the way? Is that not great? Yes? Okay. Well, let me know if not. The basic vertex for that UV theory is the coupling to a gauge boson, the W. And that vertex looks very much like the vertex in QED. With that convention, that will be minus I gamma mu P left, and the coupling out front is G over square root of 2. Something else we'll need, and something that I've done here but I haven't told you about, is that we're sitting in the Feynman gauge for this W boson, just to make our life easier. But when this propagates, that is when it's an internal line, this will be minus I eta mu nu for the 2 indices of the 2 vertices over Q squared minus M capital MW squared. So that's for the UV Feynman rules. I'm assuming you're somewhat familiar with the Feynman rules, but if you want me to go into more depth, ask me about it now or later. You can derive the same thing, put in those operators in between matrix elements of in and out states. We'll sometimes do that. And now in the EFT, there's a single term, and its emission conjugate. But if we look at it, now we'll have 4 fermions in it. We can draw it like this. In this case, by the way, if you want to put names to things, you can say this is a U bar coming in and D bar going out, and then this is a W plus, just to conserve electromagnetism, although it can be derived from that very formula without thinking. And for the EFT, we have the same thing, UD, and then also that same vertex will give us now UT, a neutrino, and a positron, if you think of it going out. And the Feynman rule for that will be, again, will leave us a gamma matrix in there, and we just stick an I in front of G Fermi for G Fermi to the square root of 2. And then let me write that structure in this tensor form. So there's two gamma matrices, but they're not multiplying each other. They're in different spaces, so I write that product in there. Right, so not too much, the two of them. We're going to do it diagrammatically at first, although later on we'll move on to other ways of doing things. But basically, this Fermi interaction that is 4-point, we now know is mediated by the W boson. So let's compute sort of that same 4, not that one. I want to think of, maybe I'll do that one. Maybe I'll do that one. That same process when it's mediated by the W. So let's write that Feynman rule. So this is going to be, sorry, you can't see that. Now we do the diagrammatic matching. And on the one side, we write the Feynman rule for this process. U, T, W propagating, neutrino positron. Right, so two vertices, one propagator, everything together will give us I minus IG over square root of 2 is what came out of each of those vertices. Why am I using green now? Minus IG over square root of 2, gamma mu left, and then another one, gamma mu to left. And they're connected by the W propagator, that line which comes with this Feynman rule. Minus I eta mu nu Q square, or K square, what we call the low energy momentum, minus MW squared. I'm cheating a bit. If I'm talking about amplitudes, I should contract those gamma matrices with the spinors for these guys. But what I want you to realize is that will be the same spinor structure where I'm talking about this full theory or that full theory. So I'm not interested in those spinors. I'm just interested in the coefficients that they have. So I'm not going to write them, but you could go ahead and do it if you back by it. Now what we do is try and connect these two. But as they are, I cannot connect them right now. So if I equate this to that, I realize that this is a constant independent of momentum, whereas for that one, we do have a momentum dependence in the propagator. So they're not strictly the same thing, but what I do is, of course, as you might have guessed or not, depending how awake you are, is to expand on the small k versus m. Right, so that is, in this analogy, that would be lambda will be the mass of the W, and k, the scale at which we're looking at it. So it's much slower than that. Eventually, it will be in the EFT. So we expand on that, and then I write that this is. Let's see if we get all the minus signs right. 1, 2, I G over square root of 2 squared. Eta mu nu will contract those vertices, but also we will have, when I set k to 0 in that expansion, minus mw squared of the gamma structure. Alrighty? I hope you're with me so far, but if there's any questions. maybe as Anish did this, I'm not sure, but this lecture is about actually computing step to step, so that's why I'm going through it. Righty, so now I look at this, I equate them. What is the conclusion? The conclusion is both of them have a minus sign, luckily, because G Fermi is defined positive. So I get that 4 G Fermi over square root of 2 equals G squared over 2 MW squared. Okay, so unless I did anything wrong in there, but I didn't. I can also tell you that the mass of the W in this convention is proportional to a BEF B and G over 2. Well, this is, connected to Tim's lectures. That's how they get the mass in the standard model. And all of that will lead us with a bit of algebra to the expression G Fermi 1 over square root of 2 V squared. Okay. Let me know if any step is, well, tiny bit of algebra is kept in there. You can do it when you, I don't know, in your head probably. Or in a piece of paper. I don't trust my own head to do those things. But I hope the procedure is clear. We have the diagrams, we match them in our expansion. Again, EFT has an expansion, you have to expand. Once you do that, you can find G Fermi as a function of, well, factors of 2 are irrelevant in here, coupling square over mass squared. And at low energies, please note that we only know that combination. We don't know separately the mass. Yes, is that a question? Yes, because those will be in our EFT expansion. Those terms that I don't have in there are higher derivative terms. So we're expanding K, those will drop out well. Thanks for the question. Righty. So I would say we only know the ratio of these two, and in fact we only know, you can put a number in here. This is 10 to the minus 5 GV to the minus 2. This is G Fermi. You can look it up. And it has a scale in it, but it's not a mass scale, it's this ratio. So just by knowing G Fermi, just leaving down there in the EFT, we know there's a higher dimensional operator. We know there's something going behind it, but we don't know exactly what is the mass of the particles involved, only that ratio. And if you, I don't know, if you take V, in my convention, I should also say that V is 246 gigaelectron volts, and the mass of the W, as you know, is 80 gigaelectron volts. So they're not walls apart, but they're not the same number. Righty, now, the first problem for you guys to try in this lecture number 2 is to do the same thing with functional methods. That is with the path integral approach. So we'll revisit this time and again. Yeah, let me do that first. We'll revisit this a few times, but the path integral approach, as it often happens, is quite intuitive and easy to grasp. The generals of it, the particulars, not so much. But if you believe me for now, I can say that the EFT action will just be integrated over the W fields on the full UV theory. So intuitively, do we see the W's? No, we don't at low energy, so let's just sum over them. They're virtual particles, so that's what that sort of equation can be interpreted as. We're going to do it at 3 level for now, later at 1 loop. There will be renormalization and corrections to be done there, but for now, we live happily at 3 level. And at 3 level, this can be expanded as the UV action evaluated at the solution of the equations of motion for the W. That's what I call W sub EOM. And I tell you this, but I don't justify it. The corrections to that will be 1 loop. So the exercise for you is to do that, to solve the equations of motion, and I'm going to be nice to you and give them now explicitly. You know how to do this, I'm sure. Euler-Lagrange equations, the form they're given is even simpler to derive. It's just the partial square, W mass squared, acting on W minus, let's say, minus G over square root of 2, J minus mu equals 0. So that's, well, actually, let me put the minus on top. This is, if you want, the definition of EOM. It's even simpler. You can, I mean, it's, because again, it's a derivative expansion, you could even drop the partial, and this turns into an algebraic equation for the W that you can plug in there. Again, just being consistent, neglecting the derivative square in there. But if you just do that, neglecting, so you can set derivative square to 0 everywhere. And at this level, it will work, and the whole thing is rather simple. You'll get out of that an effective action. What is the name I give this? I don't think I give this a name. Well, yeah, you get an effective action which contains the term b4x, some coefficient. Let me call this C for now, it doesn't matter. J mu is the contraction of those currents. And you can sort of fit, you find a value for C, that's what the problem is about, finding C. After doing that, then you compare with the effective action we started with, and that coefficient, and there will be, it'll give you that same relation between G Fermi and the masses and coupling. Righty. That's a calculation. Let me say a few words about the physics, but any questions about the technical aspects of, or any of that? Right, so please do try that. Maybe you have done this already, I don't know. This is a quite typical example. Now about the physics of it, if I look at it and I wanna, I don't know, have free time and I wanna speculate about what's going on in here, the typical argument is because at low energies, we don't have energy enough to resolve the W. If you think of the LHC as a humongous, or particle experiment as a humongous microscope, looking at high energies, low scales. If I don't have enough budget to build a big experiment, I don't have enough energy, and what I see in practice is a 4-point interaction. I don't have enough energy of small distance resolution to see the W in there. Now, if I increase the energy, I reduce the distance, I'll open up that operator to see that there's an actual W propagating in there. I'll only see that when I have enough energy to produce the W, to reach the mass M. Or if you want to go up in scales here to reach lambda. It's a bit, so the sketchy way of it, one can actually also turn this into a bit more quantitative picture in position representation, and you can see that a potential of a massive particle will give you something like, in 4 dimensions, or space-time dimensions, the exponential of minus W mass times distance over distance. And that's interesting, at least I find it quite nice to connect with the quantum mechanics example we saw before. We're trying to model these short distance effects with delta potential, square wells, and crazy things. What is the actual short distance potential that nature produces? Well, something like this. So it looks like a Coulomb potential, but with some exponential element. That means that in practice, if you're at distances smaller than NW, you will see that 1 over R potential, but as soon as you reach, or you go to distances above, the inverse of MW, the whole thing will go to 0 really quick. So you don't see that potential from large distances. Great. Now we move on to our soon to be beloved and appreciated example of a scalar, complex scalar. But that's going to be quite a change of topic, so any questions about this part? This potential. No, this potential is in general for a massive particle. The extra complication, I think that is not straightforward in here, is that the currents for the weak interaction are not conserved until vector weak symmetry is breaking. So I cannot really put two sources there to see this type of potential. But if you instead have, say, I don't know, a massive axion or other particles that coupled to currents that we can sort of engineer in the lab, then you could see potentially potentials like this, or massive gravity construction will give you also things like this. Okay, so now for the same thing, but in a simpler scenario somewhat, let me introduce you to our complex scalar theory that I'll be using in a while. So we're going to use, I think we said this already, but the complex scalar we'll call phi. At times, we find it more useful to work in terms of the real and the imaginary part of it, which we define as 1 over square root of 2 of phi 1 plus I phi 2. We also assume it has a abelian symmetry that will be preserved, a global one, that sends phi to pick up a complex phase. And you can amuse yourselves to see that that same transformation in terms of real and imaginary coordinates is an O2 rotation. And just one more notation thing, I'll use phi star phi and a partial derivative with an arrow left and right as the derivative acting first on the left and then on the right with a minus sign. Not sure if you're familiar with the notation, but that's somewhat, it's easy to find. All right, so then what is our EFT action that we'll be using over and over again? Well, let's just write it in full. And please record this with fire in your mind because we'll be coming back to this again and again. Kinetic term, mass term, phi for interaction, normalized with a factor of 1,4. That is what I'll call the renormalizable part. And then the first EFT corrections will look like all of them with 1 over lambda squared, C6, for a potential-like term. With 3 powers of that, so there's like 6 fields in it. And then we'll also use CS lambda square of 2 fields only, or 4 fields only, sorry. That's derivative square acting on 2 of them. And then CG for that left-right derivative acting, and the whole thing squared. Again, I hope you'll forgive me when I write a current square, J mu is J mu contracted with J mu with the metric, but time is at the essence when you want to calculate. And then just for establishing the notation, I said I'll call this part S4, which is the integral of a L4 action. Sometimes I'll refer to the others as, for example, by the subindex in the CG. So that will be LG. Just bear with me, it's just notation. There's no physics in it for the moment. And I am assuming you have seen a few things about EFT. These 4 in particular dimensional analysis that tells me all these three operators that I wrote in there because of the dimensions of phi and derivatives, which are 1, should have an inverse double power of the scale in them. There's another question as to why I only these three. I use only those three, but that question is for Joy lectures when we reduce it to the minimum number of them, but we'll also see that with equations of motion. None of that quite yet. Right, so now we're good with time. Now let's go through a number of UV models that will match onto this theory. So imagine yourself as an experimentalist living at low energies. You have seen interactions of this complex scalar phi. It might be charged under some, or it is charged under that global symmetry. And as we wrote in the first lecture, that phi will be quantized with creation and annihilation particle and antiparticle operators. You can think of scattering and finding those matrix elements to have an idea of what those couplings are. And now next door to you, there's a series that has, there's three series, in fact, and you'll ask each of them what is the UV completion they think this is coming from. Righty, so series number 1 tells you that there is a heavy singlet S, sorry, that S is different from the action, but I don't know, the surname might start with an S, so they gave it that name. And the UV model for this S theory, let me put a superscript S, it doesn't really matter, but and the UV theory they write is before X, let me just write S for UV. So that is that same renormalizable action for phi star, but with a subscript or superscript UV because the couplings might not be the same. So this is the same as, let me say that explicitly. S4 UV is just S4, which I change M square to M UV square and lambda to lambda UV square. So it's just relabeling, but it were important because they're not the same as what we encounter in the EFT. And then for the action of the singlet, that happens to be this partial square. It has some mass ms squared, and it has a coupling to the scalar field in a potential like with some coupling kappa. Please don't confuse that with k, the mass of it, and then s phi star phi. That's all there is. Now they tell us that ms is much larger than the mass of the complex scalar that we see for whatever reason, and we'll do the same type of matching that we did before. Take a very large ms, integrate out, that is, solve the equations of motion for s. That looks something like this. I mean, I'm sure you know how to derive them. And then put them back into the action. That is the second exercise for you to try. And in that same expansion, it is very much like the one you're meant to do earlier for the W boson, but even simpler in some sense. But now you do have to retain those derivatives, partial squared, because what one gets after doing that is the following. Let me call this S EFT, which is what we obtain after doing that. Plugging in the equation of motion, and there will be S4 UV as before, but the extra terms we'll get, so one of them is kappa square halves phi star phi squared and then minus kappa squared lambda squared halves, well, ms squared, sorry. Of phi star phi. Okay, so now as it happens, the first term that we get when we solve for that is, it looks like that phi-4 term we wrote in the beginning. So now as we do, this is a matter of equating actions time and again. We can look at this contribution plus what we call the UV in there. That was just a simple shift. And then back at what we defined as original action, where we had that same operator, derivative square acting on those guys, but we call the coefficient CS over m lambda squared. Okay, so, and the lambda in there. So let's see if we can see this, but so the thing will be to equate those two actions. That will give me, for the phi-4 term, we'll have lambda. So this is by equating S EFT S and the S EFT we had. I'm finding how to reconcile the two, then you'll see that the first, the coefficient of lambda phi-4 in there is minus, phi-4 is minus lambda fourths. In here it will be minus lambda UV fourths. And then that extra contribution of kappa squared halves. Right, so for starters, the quartic coupling is not the same in both theories. It's corrected by that term, but when you're at low energy, you don't care about, an unknown being the sum of two unknowns. Is just an unknown that you call lambda. And then you see that you don't produce C6, so we set that to 0. That's CC. You don't produce CG, so we set that to 0. And then the only non-trivial term is C, what do we call it? S over lambda squared. Let's stare at it and at this term, and that will be, okay, this is an awakeness check. Kappa squared over ms squared with what factor up front? Minus a half, correct, very good. You are awake. But you see how this is done, no? Just equating the two actions, finding what the coefficients are. So that's our first matching exercise, and it's relatively simple. It's just these theories told us that there's a heavy singlet. We can integrate it as we do and find those coefficients. And that the prediction of that theory will be that there's only one operator produced, the other one's a 0. Very good. Now we move. Yes, so this one thing that I've done here that is I haven't justified is that S phi star phi is dimension 3. So you need a scale to put in there to make it dimension 4. What I chose to put in there is ms. If you choose another scale, you could, I don't know, you say I choose m. In that case, you'll get the ratio of m squared and ms in here, so an even smaller contribution. This is all normalization in that sense. I could have called it something else. The important thing is that you don't, say, violate unitarity or anything. And if you look at the unitarity bound on kappa square, this kappa square has to be smaller than 8 pi or something like that. That is the one thing to be mindful of. Yes? At loop level, it will work correctly, yeah. We'll see some instances of that happening, yeah. But at tree level, the mass, in this case, doesn't get any correction. I mean, you could also question these theories as to why did they choose this coupling in particular, It could be others. I don't know, there's justifications, but we need a concrete example, and that's the one we chose, or the one they gave us. Righty, so one door down, there's another theory that tells us no, that complex field is a Goldstone boson. And it comes from maybe some spontaneous symmetry breaking, from some strong dynamics. When matching to the EFT, we don't care exactly how that happens. We just care about its group structure. And its group structure, well, I don't know how much you know about Goldstones. Counting Goldstones is rather easy. You give me the full group and the broken group. I take the difference in generator numbers, and that is the number of broken generators. So we need something that gives us 2 degrees of freedom because this guy is a complex field. So a simple instance will be SU2 that has 3 generators broken to U1 that has 1. That will do the job. You can entertain yourself as to what groups you will need to produce, say, 4 Goldstone bosons, as in the Higgs doublet, and that goes down the route that that Alex kick-started a few years back. Well, more than that. So now let's briefly go through CCWC. I don't want to, it's a bit of a technical part of it, but I do want you to at least have seen it once. Well, you saw it with Anish to some extent. Well, then, if some of these things are trivial to you, all the better. But it's never bad to see things twice. Righty, so those are the Goldstones. A bit of notation, I'm afraid, will be necessary. So this is going to be maths for a few minutes now. And this is true for any group structure, not just that. An element of the group can always be factorized. The element we'll call G. Capital T, I'm not sure why I used that, but that's what it is now. Can always be factorized into a broken and unbroken part. I'm going to call the broken Gx and the unbroken G lowercase t. To be a bit more specific, there's going to be generators of that full group, original group. I'm going to call them capital T, and they'll consist of broken generators X and lower t unbroken. Color. And so what I mean by those belonging in that part is that these guys are exponentials. Can be written as exponential of those generators. Now, our Goldstones live in the broken part of the group, so we can write them, and we will, as C, this Greek letter. And you can think of this as field-dependent group, broken group element. What we need now is to know how it transforms. And we'll be using unitary representation. So all of these guys, G dagger equals the identity for all of these. Now, how does it transform? Well, it is a group transformation, only field dependent. The pions are in there if you want to think about QCD. As a group element, you can think of what happens if I do a transformation. Well, something goes from wherever it was to a matrix G in it. In our case, will be C. What happens if I do another transformation? We'll use matrix multiplication. Multiply G on the left-hand side. We're taking the action of the group coming from the left on whatever state is in here, but I don't write the state. And now this, the outcome of these two transformations should itself be a transformation that should itself be decomposable into this factorized form. And that's what we'll call the transform C prime times an unbroken element of the group that are called little h. Now this is a transformation rule, so I can just solve for C prime. So that will give me that C prime that in the sketchy or the lazy language that we use in physics, in a transformation we say that C prime is what psi goes to under action of the group. Sometimes it's better to call things differently, but anyway, that is G, the original C, and H minus 1. Yes, sir. I multiply by H minus 1 on both sides, I get that. Now, the tricky thing, if you want, about constants is that for that to be true, which is to say the left-hand side is in the broken part of the group. The right-hand side is not so evident. It's a full element of the group G. This is constant, if you like, times psi times the broken part of it. So for this to again be unbroken, for this to be on the broken part, G is a constant, but H has to be field dependent. So secretly that depends on C. Not secretly because I just told you. How does it depend exactly? You can work this out at least order by order with generators, expansions, and that's for some groups it's done in the original CCWC paper, which is what we're reviewing here. Sorry? H depends on this same constant, C. G is a constant. G is an element of the group that we just took in here, and that's a constant, so to speak. Just like if you're thinking of for example, the type of transformation that Tim talked about, that's the same one you'll have if you have a linear representation. Let's call this psi. That will go to G psi. Yes, so this, right, that H also depends on what transformation you're doing explicitly. It will depend on both. Again, G you can write as an exponential of generators times parameters. That will also depend on that. In fact, I'm doing this over and over again, but I can refer you to my notes where I do go through some of these, at least the expansion of these to a few terms, and you see how this depends in the end of structure constants and those parameters of the transformation and C itself. And yes, I was saying the original CCWC paper, they did this for certain groups, and they found that you can write this in terms of hyperbolic sines and cosines. Righty. So now the complication from that C is that we want to write an action that is invariant under the full group, and that field dependence will be a bit annoying for doing that, because not for constant terms, but there's not much we can do with psi itself while being invariant. Say, I mean, I know how to build an invariant right away with psi. I know how psi transforms. If I just multiply by psi dagger, all of these G daggers in their mission conjugate will cancel out. So that is an invariant. So that checks out. It also is the identity. So not much to do about that. To have something that is non-trivial, I need derivatives on it. This is the reason why goldstones don't have a mass. They don't have a potential. There's no way to build something without derivatives. I can do the following: partial mu on psi, something that looks like that, but with psi dagger on the left. This would almost transform like we would like it, but the derivatives also hits H in that transformation. So this, let me say this, goes to the way I define things. H, I can substitute H minus 1 for H dagger, by the way, and that will be H on the left, right, speed up that term. Like that. No, minus 1 is on the right. Not that it matters much, but anyway. And then psi itself. Okay, it's a good exercise to do. G itself doesn't depend on the field, so the derivative will not act on it. But the other on H it will, and it gives us that terms that if we now say take the square of Z or this times this emission conjugate, those H in this case will cancel out, but not for that other piece. But one can realize that this piece, because it's all purely unbroken elements in there, this lives in the unbroken group. So this is unbroken element. I'll give you a bit more justification in a minute. Well, it's this other one. So inside of it, it will be broken part of the group, psi times psi, but we also have H and H minus 1 in there. But because of the commutation rules of the group, which I haven't given you, let me put them here. We have that T commute with T goes to T, of course. It's a closed group. It's the unbroken group. But this and fully antisymmetric structure constant means that T and X goes to X. And you can rewrite this as a series of nested commutators, and this gave you that formula. I'm going to remind you of it in a minute, but that means that this is in the broken part. So we can reach the end of this road, and I'll just define U mu A as the projection, and I do that taking the trace of broken generators on psi dagger. And that's really all we need to build invariant, or the ones that we'll be interested in our case. Well, and that A index is an index of the generator. Now with that we can, so for example, we could build an invariant and we will in a second for our particular case as minus. We need some constant because this is just dimension 1. U mu A sum over A. Where this part can be rewritten so that it's a little clearer, I write U mu as U mu A times XA, the sum over there. That thing can be rewritten as a trace of U. So that invariance is more evident. Right. So that's CCWC for you in 5 minutes. There's a lot to digest in this. Don't get me wrong, this is complicated stuff, but that is what we need for our EFT. But any questions about that bit? Okay, then let's get to work on the matching. For which purpose we just plug in the generators of our example. Straightforward, and we'll also need that one formula that I saw Anish gave you, but I'll remind you of. Now we talk about SU2 over U1. Now with this formula, e to the minus a partial mu of e to the a is the sum over n of nested commutators. 1 over n factorial minus a dot 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 commuted with partial of a, and as many brackets that we need because there's n commutators in there. I will have that. Psi for us is the exponential of e to the sigma dot phi times f. These phi are the real and imaginary, or they will be the real and imaginary parts of phi, where phi dot, that dot product is just the first Pauli matrix, phi 1, plus the second Pauli matrix times 2. It is in the notes, and I'm sure you've seen the millions of times as the usual Pauli matrices, 0, 1, 1, 0 for the first one. And anything else you should know? Not really. You know how to commute them. So another exercise for you is to reproduce that UA defined as the trace of sigma A halves of, well, psi has an expansion in terms of Goldstones. In fact, you could actually derive the full relation. You can sort of do that exponential explicitly with the gamma 1 and gamma 2 functions, but we only need the first few terms, and those will return, and you can check this as an exercise, I times partial mu of phi over 2 f. There's not 2 in here, what are you talking about? And the next term will be 2/3 of f squared with a minus sign, or a plus sign for now, partial 1 2 with that left and right arrow times the Levici beta E B3A by B plus higher orders in 1 over F. Okay, so then one can put that back into the original action that we had, so the trace of UU or the sum over A of those guys. The first piece is actually going to be a kinetic term with the right normalization, and that's why we chose the prefactor. The second term is going to be, and you can check, minus 2 over 3 F squared. And I know I'm out of time already, so I'll try to 5 minutes. Okay. Question? Of the square of that current left, right. The whole thing squared. Okay, it's perhaps not super easy to see, but working through those Levici beta terms, summing over those indices. I'm going through this, again, another exercise for you if you have the time now and later. That's what one gets. One little bit, extra bit of information is sort of type of computation that you're doing there is that epsilon AB3 by A partial mu by B equals, well, what we just defined as that, by 1 partial mu left, right, phi 2, which also one can write as phi. This is the transpose of it, if you think of it as a matrix, times T partial mu phi. And finally, what we want for our matching is also phi star partial mu left, right, phi, with a factor of Is there an I in there? Possibly, but I forgot it. Yes, there's an I. Alrighty, so at the end of our hardest road, we can put that back in here. And now we just left-right current squared. And finally, what we want is to equate that to this original and always present action with those three higher dimensional operators and identify the coefficient that are non-vanishing. You can see that that's the current squared. All the other ones are 0. As, again, our Gaussian has no potential, so we won't get a term of 6 fields like that. And if you do the matching, and you can maybe, right, we'll do this and we'll stop. Let's see if you can see the matching from where you stand. Again, it's equating that to that equation once we sub in those expressions. We'll have that CG over lambda square is going to be equal to all those factors of 2/3 that I'll square. Anything else? Right, so that's the question for you to answer. If you answer it quick, you can go away faster. So what's the prefactor in the right-hand side there? It's tricky. You have to do that substitution there. And that's my time. Okay, just to get you right, I need to sub in this. In there and compare it to that. +1, yeah, it's and clearly simple answer. Yeah, you put I squared, cancel the minus sign, and you get that is the matching for a Gaussian boson. The third example that's in the notes, and we definitely don't have time for, is the case in which there's an ADS slice, with two scales associated with it, and there's this dual of a CFT picture of it. What's important for us is that there's two scales, and in particular below the lowest of those scales, just like for any other case, EFT would apply. So we can take those predictions from the ADS-CFT correspondence, get, in this case, expressions for the two-point function, which is produced by this scalar phi coupling to a non-perturbative CFT sector. We just actually borrow them from the tacit lectures by Tony Gergetta, and then expand again for small k and match onto these coefficients. And you'll see that in that case, you get the phi to the 6th term. But it is in the level of complication, that will be the most complicated example. To do that type of exercise, I did it. I used Mathematica because it was a bit, getting a bit unwieldy. But the basics of it is, again, match finally to this action just as well. But if you have questions about that third term, please do approach me after this, and this ADS CFT we can discuss. As much as I know, I'm not an expert of it, but this problem in particular we can talk about offline. And I'm sorry for taking more time, but I'm happy to take your questions. In the third case, no, you only generate this term. I'm sure that you can build some. Yeah, I think you can. So we're taking pretty simple theories to be our UV theories, but you can complicate them further, and I'm pretty sure you can generate all three of them simultaneously if you want to. So they're different. So if you want to think about this, and maybe Anish introduced that in that sense. So if you want to think about sort of some UV completion of this UV completion, or a way to think about that, you should have to start with, for example, a full SU2 doublet, but let's be careful to call that something else. Psi, which will have two components, psi1 and psi2. I'm using psi, but this is a scalar, so sorry about that. But that will transform under the full thing. And then you can rewrite that as a unitary matrix V and sort of a modulus, just like we do for the Higgs. In fact, we're going in that direction very much. So this is like going from, those are complex terms. They have two components each. You can always write that as a unitary matrix with three components in them and a radius, if you like. Now I can further decompose that V into a broken, the way we call this, Vx and Vt. So what I'm saying is that the degrees of freedom in Vx are the Goldstone bosons that we'll see. The other two are heavy, and in this context, they won't show up in there. But these are, for the UV completion of that, you'll indeed, like you said, need full SU2 representations. But what we're picking out after this breaking, just like in the Higgs doublet case, is not the full doublet, but parts of it. In the standard model case, it's the three Goldstone bosons that go to the W on this set. In this case, because of the breaking, it's just two of them that happen to be, well, that we have to associate with the two complex degrees of freedom in there. And that will be one of those instances in which just identifying degrees of freedom is not a trivial process. Just like in QCD and the Carrel Lagrangian, what we see as those Goldstones, those pions are actually QQ bound states. So in this, so for example, for the singlet case, we just wrote a UV model that was the same piece plus the couplings of S. Now what I'm calling the UV model for this other case is just the action for a Goldstone boson, which is that piece here. So there's no S4 in there yet, because the Goldstone boson Lagrangian itself contains the kinetic term for the Goldstone boson. So this, and I'm already writing this from that point of view in terms of the Goldstones of the theory. So all of those heavy states, the H is a bad name, but all the other degrees of freedom are sort of already integrated out. So this is itself an EFT, so it's a double layer. No, they just have one abelian phase. This is not SU2. This is just a simple, complex scalar field. Real and imaginary part, but this is just a U1. Symmetry, sorry. This is just a U1 and nothing else. And in fact, that U1 is going to be the unbroken part of the group. Yeah, sorry, it was a bit confusing, this. Yes, very good. There's things that I swept under the rug, and is that this cannot be, either declare them to be really Goldstones, and that would also mean that I have to set m squared, lambda, everything else to 0. If I want to give them a mass, I should postulate a mechanism that does that, because that's original symmetry forbids it. But that's something that, again, nature can help us with. The pions themselves are not exactly massless. They pick up a small mass because there's explicit breaking of the symmetry. Explicit, but small. So we can still expand on action that respects the symmetry at first. This Goldstone boson would. And then we introduce, Nis was talking in terms of chi, small spurion that breaks that symmetry and will give masses to our Goldstone. So you can do the same thing for this in this case. Yeah, so there will be higher order terms, but you're right. This, and again, in this simplistic example, we can take, well, yes, those covariant derivatives, or we can take covariant ties or symmetrize as an EFTs and build higher orders. But if we take those type of terms, will give us higher order corrections in that sense. But the full Gaussian Lagrangian, and again, there's good literature for this. For example, you can go up the paper Higgs as a Gaussian boson. Reviews about that will contain more information about how to build this Lagrangian and higher order terms in there. I'm giving you a baby problem in that sense, but it has all the basic ingredients already. Right, so let's say, we know that this is an element of the group, and again, we chose the exponential parametrization as we did in here, but we discussed yesterday, well, there's other ways of writing group elements that are not with exponential. Weinberg came up with this square root parametrization. If you do that and you do it with some of the fields, you can go through sort of the same process and they will look a priori different, but let's say we rewrite it in terms of some other field. I don't know, some function of pi instead, but that also lives in the unbroken group. So the statement that I'm giving you, but I'm not proving, is that you can go through those and write again an invariant first derivative square term. The statement is that the statement is that, the Lagrangian might look different. The kinetic term you'll normalize, so that first term as usual. The higher order terms will look different indeed, but when you compute a matrix element, the matching, actually the matching will be the same. Maybe F, if you call this F something else, we might look a little different, but the fact that expanding that, in fact, that's the power of EFT now. The fact that if you expand on that, this is the only action at order 1 over lambda squared and has a single coefficient for that current squared. There's just nothing else to match onto. So you'll get, again, a contribution to this. It is when you go to even higher order in that expansion with 6 fields, that different parametrizations of your theory will give you different ratios of the 2 coefficients. And you can use those ratios to tell them apart at the level of the matching. But again, to bang the message home, at the level of the S matrix element and amplitudes, they will still give you the same. But it's true that the matching might look different, and that's an excellent question, because at the level of the action, theories with field redefinitions look different, for example, but again, they give us the same physics. But yeah, thanks for that question. Thanks.